Hello students, welcome to EPG Pathshala. I am Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University. Today we are going to talk on the module second quantization under the paper solid state physics. Now after completing this module, the students will be able to learn how quantum particles can be described as wave functions. Second, learn about symmetric and antisymmetric wave functions. Learn that fermions are always in antisymmetric state and bosons are always found in symmetric states. Also learn that two identical fermions cannot have the same eigenvalue of any operator whose eigenvectors describe the physical state. This is known as the Pauli exclusion principle. The object of many body physics consisting of studying interacting many particle systems of electrons and nuclei. An accurate description of such systems require the solution of many particle Schrödinger equation. In principle, the n-body wave function in configuration space contains all possible information, but a direct solution of the Schrödinger equation is impractical. It is therefore necessary to work with quantum mechanical operators and wave functions, which is the second quantization. Now about quantum particles. Quantum particles cannot be described using point positions and momenta, and they do not follow definite trajectories. Rather, they are described as wave functions, and when these wave functions overlap, they mix, so that if we make a position measurement and find a value in the overlap region, we cannot say if it is particle 1 that is there or particle 2 if the particles are identical. Now consider two spin half particles which are identical. Now suppose we observe that one of the particle has a sz value of ma h cross and the other with mb h cross, such that ma is not equal to mb. The state vector after measurement can be written as the first state vector as shown, with half ma and half mb, or we can interchange the positions half mb or half ma. Now under the heading of quantum particles, students, we now consider the quantum case. So the two state vectors which we had mentioned earlier in the quantum case are not physically equivalent. So you try to understand, students, the difference here now between the classical and the quantum case. Also note that the two ket vectors xi and alpha multiplied by xi as shown are physically equivalent for any complex number alpha, right? But the expression that you see, the ket vector for the two particles being represented by half ma and half mb, is not equal to alpha times the ket vector with the two particles being reversed. That is, now the first particle being half mb and the second one being half of ma. So you understand the difference now between the classical case and the quantum case. So students, continuing with the study of the quantum particles, as we have seen that in the previous example, the dissimilarity between the classical and the quantum case, and keeping that in mind, let us construct the state vector in the following way. So this ket vector that you see here, again we take the case of two particles represented by ma and mb. So here the capital Xi, the ket vector, is equal to some constant C times the ket vector, that is half MA and half MB in the ket vector, plus C prime times the interchange of these two particles as shown, that is half MV first and then half MA later. So you see here that now we have something like this, that the total ket vector of the system consisting of the two particles is something like a superposition state, where the first is, as you see, multiplied by a constant C, and the second one the C prime, and which of course we know that the C and C primes are, we still have to determine them. Now the above state vector that I have just mentioned can be made to satisfy a condition which we had mentioned earlier. Ket vector, the new ket vector rather, is equal to alpha times the ket vector by interchanging the particles. So the earlier ket vector was not able to do that. We were not able to satisfy this condition. So we made this new one, and this new one can be made to satisfy this condition, the second equation shown in this slide. Now that we have constructed the ket vector and that we want that the ket vector should satisfy the condition that the capital Xi, the ket vector consisting of two particles, should satisfy that this new ket vector should be equal to alpha times the ket vector with the particles interchange. For that, what are the conditions? And these conditions is being imposed on these constants C and C prime. Remember that. So we have to choose the values of C and C prime in such a way that this condition is satisfied. So this requires that C should be equal to alpha times C prime, C prime should be equal to alpha times C. So this implies then C prime is equal to alpha square C prime. So this means that alpha square is equal to 1 or alpha is equal to plus minus 1. Or in such a situation, then C is equal to plus minus C prime. So you see that very nicely, by imposing this condition, we can satisfy the condition which we had previously mentioned. Or rather, we could say that if we want to satisfy that condition which we had previously mentioned, then the C and C prime in the new ket vector should be satisfying this condition, that C is equal to plus minus C prime. Now you can see from here that there are two possibilities, that C can be equal to plus C prime and C can be equal to minus C prime. Well, obviously this gives rise to two possible conditions then. So the above analysis generates two possible physical states, right? So that is, in the original new ket vector that we had actually introduced, that now becomes two different physical states corresponding to C equal to plus C prime and corresponding to C equal to minus C prime. So explicitly then, as we see in this case, that these two distinct physical states, one of them is called a symmetric state and the other is called an antisymmetric state. So in the symmetric state, which is now represented by S, Xi S, you can say that of the two particles is proportional to then the first ket vector plus the second ket vector with the particles interchanged, right? Antisymmetric case, which is now the subscript A, as you can see, tells you the first vector minus the second ket vector with the particles interchange. So you see that this analysis then for the quantum particles generates, for two particle case, two possible symmetric and antisymmetric states. So students, let us now discuss the Pauli's exclusion principle. First, the fermions, which are particles with half integer spin, such as electrons, protons, positrons, etc., are always in the antisymmetric state, and bosons, which are particles with integer spin, such as photons, phonons, helium-4 atoms, etc., are always found in symmetric states. Now, let us suppose that if A is equal to B in the ket vector which we had introduced earlier, then in the symmetric case, when A becomes equal to be, then the symmetric wave function would be simply the ket vector AA. But on the other hand, the antisymmetric ket vector would be equal to 0. Thus, for fermions, two identical fermions cannot have the same eigenvalue of any operator with eigenvectors describe the physical state. This is known as the Pauli exclusion principle. Now, what about permutation operators? Consider two distinguishable quantum particles and an operator omega, whose eigenvectors will be used to characterize the states of the two particle Hilbert space. Suppose we perform a measurement and find the particle 1 has an eigenvalue omega 1 of the operator capital omega, and particle 2 has a value omega 2. The state of the system would be after the measurement. This, that is the ket vector, will be simply omega 1 omega 2 ket vector. Now let us define a two particle permutation operator P21 and let it act on the ket vector omega 1 omega 2. As a result, when P12 acts on the ket vector omega 1 omega 2, what happens? The omega 1 and omega 2 are interchanged. That is, now the ket vector will become omega 2 omega 1, not omega 1 omega 2. So continuing our discussion on the permutation operators. Now if the particle were identical, then the physical states can be written as symmetric as well as antisymmetric combination. Now you remember that we had discussed this, a case of symmetric and antisymmetric combination. So as you can see, these two equations, the first one with the subscript s in the ket vector is proportional to a ket vector omega 1 omega 2 plus the ket vector omega 2 omega 1. So this is basically the symmetric case. In the antisymmetric case, which is the second equation represented by this subscript a, is proportional to the ket vector with omega 1 omega 2 minus the ket vector omega 2 omega 1. Now let us see the result of the action of the permutation operator, which we had introduced earlier, on the symmetric and antisymmetric states. So P21, when it acts on the symmetric ket vector, nothing changes. The symmetric ket vector remains the same, which is of course very obvious, as you can go back to the first equation and see that the two ket vectors which we had written, if we interchange the two, everything remains the same. Now on the other hand, we apply the permutation operator P21 on the antisymmetric state, we get minus the antisymmetric state. Again, going back to the second equation above, we see again, which is quite obvious, that if we interchange, negative sign is introduced in the front. Thus, the fermionic states are eigenstates of P21 with eigenvalue minus 1, and bosonic states have eigenvalue plus 1. These are the allowed eigenvalues of the operator P21. Now students, let us discuss about the n particle states. For an n particle system, there will be n total permutations of the particles, where if they are identical, give rise to n non-equivalent states. Thus we can construct state the ket vector phi s for bosons symmetric and the antisymmetric ket vector for the fermions. which are simultaneous eigenstates of all permutation operators P alpha, where alpha is equal to 1 n. So, P alpha, when it acts on the symmetric state, gives rise to the symmetric state, while on the other end, when the P alpha acts on the antisymmetric Ket vector, it gives rise to epsilon alpha multiplied by the antisymmetric Ket vector, where epsilon alpha is equal to 1, where when P alpha is an even permutation, and it is equal to -1 when P alpha is an odd permutation. Number operators and second quantization. For a n particle system, the total energy is given by E, where you see in the subscript I have written down alpha 1, alpha 2 till alpha n. So, this is an n particle system. So, these alphas representing the various particles of this n particle system, that is E alpha 1. Alpha 1 is representing the first particle, alpha 2 the second, and so on till alpha n the nth particle, is equal to the summation over I epsilon alpha I. So, that is each of these particles, they have these energies, individual energies, epsilon alpha 1, then epsilon alpha 2, so on till epsilon alpha n. So, you do a summation over the I, and then you get the total energy of the n particle system. Now, let F alpha be the number of particles occupying the state alpha. Then the summation over all the alphas, the summation over F alpha is equal to n. That is the total number of particles. And then E subscript F alpha would be equal to summation over alpha F alpha multiplied by epsilon alpha. So, you get the point. You see the first equation and compare the last equation, you will see the difference. That is, the first equation is a summation over the i's, saying that the sum of the total energies of these n particles is added up, and then you get this E, alpha 1, alpha 2, or so on. But on the other hand, if you have a distribution that you have certain number of particles occupying this certain state alpha, then you have to multiply this number of occupation F alpha by that energy epsilon alpha, which is very straightforward and simple. Number operators and the second quantization. Now, for many particle states, as we see that we can write down the Ket vector like this, F1, F2, F3 and so on. So, this F we are talking about, F1, F2 and so on, we had already sort of introduced it earlier. There is F1 is the number of particles occupying the state alpha which is equal to 1, then F2 is the number of particles occupying the state which alpha is equal to 2 and so on. Now, these number of particles which are being occupied in the respective states alpha, for bosons it takes 0, 1, 2 and so on. These are integers. So, when we have a bosonic annihilation operator B alpha acting on this Ket vector, that is B alpha acting on the Ket vector F with F1, F2, F3 and so on alpha, F alpha, then what happens is that it gives you this expression where under root of F alpha multiplied by a Ket vector in which you notice that the F alpha is not alpha F alpha anymore, but F alpha minus 1. So, that is the annihilation operator B alpha acts on the state alpha, so that F alpha becomes F alpha minus 1. So, one particle is reduced in the alpha state. Now, on the other hand, in the next equation you see that B alpha dagger, that is the creation operator acting on the same Ket, will give you a different result, then is equal to under root of F alpha plus 1 multiplied by a Ket vector, where you get to see, and compare this with the previous one, that F alpha now is changed to F alpha plus 1, that is creation operator now acts on the F alpha and it creates one particle, that is F alpha is no longer F alpha but F alpha plus 1. And in the third case you see that this is a number operator, that is the product of the creation operator on the left, that is B alpha dagger multiplied by B alpha. This is the number operator which is basically a preserving operator. Remember that this is a number operator acting on the same ket, gives you F alpha multiplied by the same ket vector. Nothing happens to the ket vector because the number is preserved, because it's a product of the creation and annihilation operator. And remember, if you look at this very carefully, the annihilation operator is coming first on the left and then you have a creation operator. Okay, this is, you have to remember, I mean, like, you have to follow this ordering very much. And at the same time, the bosonic operators satisfy the commutator of B alpha and B alpha dagger is equal to delta alpha alpha prime. So that is the commutator of B alpha and B alpha prime dagger is equal to delta alpha alpha prime. As you can see that unless alpha is equal to alpha prime, the right hand side will be 0. Now we discuss the number operators and the second quantization for fermions. So now, remembering what we had discussed for the bosons, for the fermions this F alpha can take very distinct two values only, 0 and 1. I hope you understand why it can take 0 and 1, because for bosons you see these particles can, any number of particles can occupy the same states, but in fermions this is not so. Pauli exclusion principle does not allow only two values, 0 no particles, 1 particle. So when this operator D alpha, that is the destruction operator, acts on this ket vector where F alpha is equal to 1, then it will act on the F alpha, the alpha state, and will give you an expression minus 1 raised to power n alpha, and in the ket vector what will change, that F alpha will no longer remain 1, it will become 0. It destroys that F alpha state, it removes that particle 1, makes it 0. Then on the other hand, the creation operator D alpha dagger, when it acts on the ket vector where F alpha is equal to 0, then you get minus 1 raised to power n alpha. In the ket vector, this initially that F alpha was 0, it becomes F alpha is equal to 1. It creates that in the alpha state 1 particle. Here what is n alpha? Here n alpha is equal to summation over F beta, where beta is equal to 1 till F alpha is equal to 1, and satisfying the anti-commutator, that is D alpha and D alpha prime dagger is equal to delta alpha alpha prime. So I hope you have understood this second quantization for bosons and fermions. So students, let us see that what we have learned in this module. Quantum particles cannot be described using point positions and momenta. Quantum particles can be described as wave functions, and when these wave functions overlap, they mix. Fermion particles with half integer spin, such as electrons, protons, positrons, etc., are always in an antisymmetric state, and bosons, particles with integer spins, such as photons, liquid for helium, atoms, etc., are always found in symmetric states. Two identical fermions cannot have the same eigenvalue of an operator whose eigenvectors describe the physical state. This is the Pauli exclusion principle. Fermionic states are eigenstates of the permutation operator with eigenvalue -1, while bosonic states have eigenvalue +1. Thank you.